practice it is. Let's see. Looks like we have a portion here. Looks like 100, 180 over 900. Oh, they already told us the proportion. Rachel. All right, there we go. So what's the answer? The answer is D. Yay! Let's do another one. A traffic consultant. That's not good. Right. There we go. Want to estimate the proportion of cars on a certain street that have more than 2 occupants. Stand to the side of the road for 2 hours on a weekday afternoon and flips a coin each time a car approaches. What a strange way to do it. If a coin comes up heads, she counts the number of occupants in the car. After 2 hours, she has counted 103 cars, 15 of which had more than 2 occupants. Which condition for constructing a confidence interval has she failed to satisfy? Well, it looks like she sampled 103, so A is good. Is n times p greater than 10? Yeah. And the opposite seems to be true too, but less than 10% of the population. No, there's, yeah, I think it's okay, right? We're fine with that. So I'm gonna say, well, I don't know actually. I'm just estimating. I guess we should check. What is n? N is 103, and p is. Our proportion is 15 out of 103. Approximately 0.1. I don't know, I was tempted around it there, but we'll just go around it here. So let's check out 15% of 103. That's going to be fine. And then So if the 15% works, the other one's definitely gonna work, right? So that's satisfied, that's satisfied, that's satisfied, that's satisfied. So it must be E. Weird. Why is the data not a simple random sample? So I believe that the problem is that right there. That's not going to be a representation at all. Because she's not going to get, she's getting a really select group of cards, not represented. Alright. Moving right along. We've got a polling organization. I can't talk. A polling organization announces that the proportion of American voters who favor congressional term limits is 64%, with a 95% margin of error. Confidence margin of error 2%. Which of the following statements is a correct interpretation of 95%? Okay, so I'm going to do some deductive reasoning here. Okay, so let's see. If the poll were conducted again in the same way, there's a 95% rate of the fraction of voters. Yeah, it's definitely if a confidence interval interpretation looks like they're interpreting the confidence as probability, using the word chance, it's out right away. We don't interpret confidence intervals as being probabilities, so we don't do that. So that one's out. I don't know. Let's see. If the poll were conducted again, and say probability again. All right. Among 95% of the voters. What? Okay. Yeah. All right. Okay, moving right along. So, all right. The poll in the previous one. We're going to suppose it was conducted by email, and they're concerned about the possibility of voter coverage. Since some people do not use email or have filters that block mass emails, which of the following is the best way for them to correct this source of bias? Well, a higher confidence level, I'm not sure. You might want to throw it out because I think conducting a survey by email is not going to be great. So A is a possibility. We'll leave it there. A higher confidence interval is not going to eliminate this bias at all, right? A lower one's not going to. I don't think a T interval. Okay. Would a larger sample help? No, you would just wind up with probably the same proportion of people not responding, right? So then no T. All right. Again, this is a little weird here. So, all right, we're going to look at the accuracy of a laboratory scale. Standard weight that is known to weigh 1 gram is repeatedly weighed a total of n times, and the mean x bar of the weightings okay, is computed. Suppose the scale readings are normally distributed with an unknown mean and standard deviation sigma grams. How large should n be so that a 95% confidence interval for mu has a margin of error of plus or minus 0.00. So I guess you got to, yeah, you gotta do some math. So I'm gonna have some, let's see, in this case, I have sigma, so that means that I'm probably gonna go ahead and use a margin of error where I'm going to have a critical value, star times my standard error, so my margin of error is going to be my critical value, times my standard error, right? And we would really like that to equal So at 95% confidence, I believe that our critical value is 1.96. You look at your t table, and that's going to be times our given standard deviation divided by the square root of n, which is our unknown value that we need to solve. I'll go ahead and divide 0.0001 by 1.96, which is not a real number. And, so we get 0.0. And this becomes 0.1. Something like that. Not a good number. So you know what? When we get a number that's crazy stupid like that, we should go ahead and keep this as a proportion instead. It's going to be nicer. So I'm going to leave this at 0.0001 over 1.96. And now we'll just cross multiply real quick. Because I don't want to deal with. Alright, and now I have a feeling that when I divide this by 0.001, I'll get a much nicer number. And that way I don't have to deal with all that rounding and all that stuff. So the answer is actually going to be 1.96 times 0.01 divided by 0.001 equals, well, to get that square root to go away, right? We're going to square both sides. So that's so I'm going to put that in my calculator. I'm missing a 0 here. Sorry. I got 38,416. So that's going to be 38,416. And that corresponds with E, which makes me happy. It always sucks when you do a bunch of calculations and your answer's not there. You're like, ah! No? That's what my brain does. My brain screams for a while. And then I get it back together and do the problem again. Alright. Alright. This is an interesting question. Which of the following has the highest probability? when we talk about right. Randomly selecting value between -2 and 2 from the normal distribution. Sorry, second. Let's see, value of -2 and 2 from a t distribution with 4 degrees of freedom. Randomly selecting value between -2 and 2 from a t distribution. Wait, 20 degrees of freedom. Between -2 or greater than 2. Okay. Randomly selecting a value less than -2 greater than 2. Alright. When you read this question, I hope that you see all of these normal looking curves and these shaded areas pop up again. Right? Yeah? No? That doesn't happen? It should happen. We should be at the point where you're thinking don't come to read the so I mean you could actually calculate some of these things and see what's bigger, right? But if we looked at A, so you should be thinking about, like, we're not really sure what that is, right? It doesn't say what it is. We don't know if we're talking 2 standard deviations or what. But I'm seeing this shaded area for A, right? For B, well, first of all, so here's a neat thing to look at. So I put in a lot of degrees of freedom, right? And we get a fat guy right there, or a fat little sheep. If I take this and I change it to, well, let's look at our problem. So that's as close to infinite degrees of freedom. You know, it's close enough, I guess I should say. So if we look at this, so that would be looking at our normal distribution, right? There's a pretty big, it looks like it fattens up, so there's a pretty big area in there. Let's look at 4 degrees of freedom with this. So when we put in 4 degrees of freedom, it's going to shrink this thing up, right? Okay. Let's look at what happens with 20 degrees of freedom. That's our other one, right? So it makes it a little bit larger. So knowing what happens to our to the shape of a t distribution when we add different degrees of freedom, let's approach this question now thinking about those shaded regions, right? In a better way. So that one's a little bit fatter. 4 degrees of freedom, yeah? Yes. It's going to look a little skinnier, right? And we're going between. So already the A is more, right? It's going to, because the probability corresponds to the area of our shaded region, right? So let's look at C. Between, so 20 degrees of freedom is going to be slightly fatter. Sorry, that one, right? But still not as big, right? And then if we're looking at less than 2 or greater than 2 for D, so we get our nice big round one. But still, these end tails are not going to be as large as what's in the middle, right? We already know that that's got to be at least 68%, right? We would estimate that. So not D. Still A is the biggest, right? Still A is the biggest. We look at E, and well, I mean, if C is already smaller than A, then if we put 20 degrees of freedom, these tails are even smaller, right? For 20 degrees of freedom. So the tails are smaller. So it's got to be A. All right. So a good thing to remember then, what's going to happen as you increase your degrees of freedom, your graph is going to shrink, right? There's going to be less. Sorry, the tail values are going to get smaller and smaller, right? That would be a better way to say it. All right. Where are we? Okay. Until the ceiling can hold. All right. Let's see, a 95 confidence interval for the mean reading achievement score of a population of third grade students is 44.2 and 54.2. Suppose you can compute a 99% confidence interval using the same data. Which of the following statements is true? Oh my gosh. Tell me it's wider. Oh, there it is. That's a pretty easy question. Right, 99%, all that's going to happen is the interval is going to get wider, right? Every time. Should take you 2 seconds to answer that question, right? As you increase your confidence, your interval gets wider. Find a critical value of t. Please tell me that you're getting that as well. Right? Just use your table. What is it on the table? Anybody got a table handy? 8 degrees of freedom. To the right, though, to the right of our critical value. So I do believe we are going to have to subtract from 1. So does anyone have a... What do you get as your critical value? Yeah. I'm going to take your word for it. Yeah, because you get, yeah. Because for your T score, because what you're getting is, when you go to your T table, normal was giving you this, right? But with the T table, it is actually giving you values to the right. And it says it at the top. It's got it shaded there. Okay? All right. Okay. Standard error of a mean. 9 men. We don't want the margin of error, but the standard error. Do we even need that to compute it? I don't think we do, right? Because we want 15 divided by square root n, so that's 15 divided by 3 or 5. They threw that X bar in there just to give you some information you don't need. All right. Okay. Is this the last one? Yeah. All right. Getting through it. Here we go. Did I not, oh well. I didn't put the selection.
What's this? So which of these?
And I think I closed it. Oh, well, let's see. All right. Okay. Okay, so we're looking for well, none of them have a value greater than 30, right? So because of that, we're going to need to look and see, are there outliers or any strong skewness? So this one clearly has an outlier. You're out. This one is extremely skewed. Okay, all right. So that concludes the multiple choice practice portion. We'll go over the take-home quiz tomorrow. Let you guys have the weekend to study.